sure we're going to get exactly through this integration part, but if not, we will pick it up at the start of lab. I think we can do that without grossly impacting the lab time. So let's kind of, there's too much time to not do something, so we are going to give it a shot. All right. Bunch of reading material I want you to look at, and I don't think it's particularly long, but C-test is just the look at the C-test documentation. Basically, it's out on GitLab. It is actually in the C-test repository, so it's maintained in a wiki in Kitware's installation of GitLab. So take a look at that. Look at GitHub. Particularly look at this continuous integration, right? It talks about why you would want to do continuous integration, and you just have to go through essentially this first about continuous integration block, and then go through GitHub templates, which is, I think, the next block. And what that does is it kind of talks about templates you can use to get yourself set up. And the important one for your lab is that we have a template for CMake. All right, and it'll allow you to set up CMake to do automatic, whenever you push or do a pull request from your library, it will to your repository. It will allow you to actually run CMake tests, and that's going to be important because we're actually going to work with CMake and make our own pushes and pulls. Set up, well, yeah, we'll set up some continuous integration. How did I do that? Yeah, so we'll have you set up your own continuous integration on some fairly simple repositories. All right. Anyway, going back to our integration, those are the things I want you to read about. They'll be part of our exam coming up in a couple of weeks. We talked a lot about software testing, or we focused mainly on software testing. There are, like we said, there's system integration where you take hardware, firmware, software, and pull them all together. There's hardware integration where you're throwing your hardware together and maybe putting it on a test installation where you can measure signal inputs and make sure that everything's working the way you expect it to. And then there's software integration, right? If you write a module and I write a module and we have to find out whether they work nicely together, that's a software integration. And we're mainly going to focus in that software integration, but it's important to know that all of these things exist, and all of these are very important to making working systems. You wouldn't want your car to not be integrated, right? You wouldn't want to have a set of software that's never been run on your car being installed, or run on any car being installed and running. The purpose of integration, right? It's pretty simple. We want to take together two or more software units, pull them together into a hopefully cohesive whole, verify that they work together by testing them. These can be heterogeneous components. Maybe there's some GUI code running in a front end that needs to talk to some back end code doing some finite element calculations. You could have a mix of functions. You could be in an input mode where you're entering data, or perhaps in a query mode where you're asking questions about the data that you entered previously. And every time you do an integration, or almost every time, despite how much individual unit testing you've done, you'll almost invariably find new problems that surface because of misunderstandings in the nature of the interface, or misunderstandings in the way the data is transferred. And if you do this in the wrong way, everybody goes off and develops for a year on their own, and then you pull it all together. What you're going to end up is all the problems surfacing at the same time, cascade of interdependencies, cats and dogs living together, the whole 9 yards. And that's what we want to try to avoid. We want to do our integration so that we, along the way, have the ability to self-correct and make sure before we've written 10,000 lines of code that we know how we're going to be communicating and where some of the pinch points are going to be. And that will allow us to write code that's correct far more quickly than everybody writes code that's incorrect, and then we have to go through and make it correct. A lot of different kinds of integration. We've kind of this having everybody go out and develop on their own and then bring it together all at once. It's kind of a big bang integration, right? You have a phase of software development. This is generally goes along with like a waterfall cycle. You have requirements definition. You have refinement of that to detailed requirements. You have decomposition of the software into units. You have units developed, and then you bring all the units together into testing, and everything goes badly. So big bang integration, that's kind of the model for that. Incremental integration is a slightly different model or a markedly different model. This is one I like to use. I'll often, like I said on the testing thing, I'll often say that if you're writing a project, you want to put together a thread first. You want to have your input and your output, and you want to have something coming out, and you want the simplest thing possible. Just some string, some scaffolding that you can hang code off of. And if you do this and you allow people to hang the code on the scaffolding a little bit at a time, what you end up with is with something that where each new piece comes in, it can be integrated, and all of the errors come out in a much more simple way before you end up with this huge massive code you're taking all at once. Errors are easy to isolate, find, and fix, so you have less bug loading. It's really good for an agile development cycle because the system is always kind of working. So your customers can see what's going on, and they can get confidence that you're doing what they asked you to, and you can get feedback from them as to the aspects of what you missed, because you never can grab all of the customer's requirements right up front. There has to be this give and take, and that's kind of, again, what the Agile cycle is designed to kind of tease out. Systems are complex. If you try to design them complex, it becomes unworkable because there are too many details. But if you start with a good system and a good scaffolding to start with, you can end up with a very complex system, but the system complexity can be understood incrementally as you develop the system. So it's actually a much smoother and much... whenever we do software development, we never know up front everything we need to know to write the system. There's just, no matter how much effort we put into it, this is kind of the lesson of things like the National Institutes of Health or National Health Services, NHS, over in Britain, trying to rewrite an entire or trying to write an entire EHR from scratch. You don't understand, you can't capture all the complexity, so unless you have a method that allows you to grow the complexity, you're kind of doomed to failure. And even if you were able to capture exactly what the user was thinking at the time they hired you to do the software, at the time the system was conceived, the truth is that as the system grows, the users will get a better understanding of what their requirements are, and be able to give you better guidance more correctly. There are some drawbacks. You're not going to have everything there that you need all at once, so you're going to have to write code just to do testing, just to allow the system to run that doesn't actually do anything. So in some sense, it's a wasted effort, but in another sense, it allows you to do system flow while you're actually waiting to understand and capture what has to go on in some of these other processes. Again, if you have too many developers too soon, if your thread, you have 100 developers and you have a very small code base, well, everybody coming in with their small incremental changes is still going to look like a big bang integration. But at that point, maybe it's unavoidable. We can look at it from different types. Some people like to write just the outer UI layers first, just the part that communicates with the users. This was frequently done even in waterfall systems. They would call it rapid prototyping. They would prototype just the part that talked to the users and get all of the user interactions captured, and everything behind it would just be a stub or a dummy that maybe gave always the same answer. And the idea would be that if we get the user interface so that the outputs the user wants and the input the users can provide are all correct, then all that's left is the processing, and the user doesn't need to know anything about that anyway. So it's something that we can develop more offline or without as much feedback. So that's one way of going about it. The opposite, of course, is the bottom up. You have an algorithm. You write the algorithm. The lowest layers, you have something to correctly predict the winner of every horse race, and you write that very thoroughly down at the prototyping or at the mathematics level, and then you have to build up and put a user interface around that and find a way to connect to all the big Vegas casinos and everything. So that's kind of a bottom-up approach. Or you can start with both, right? You can have the core of your algorithm at the bottom level and the core of your UI at the top level, and this is kind of a sandwich approach. Everybody grows together. And those middle layers kind of come in. This is kind of what I like to see is something where you have a little bit of everything. And this can all be done continuously, where you have a single source repository and you have everybody committing something often, right? Commit early, commit often. And since you've written your tests and you continue to write your tests, you can build your tests and run your tests every day, and you can kind of get this continuous integration and figure out what's working, what's not working. It does kind of rely on everybody having the same vision for moving forward. But if you have automated testing and you have this going on every day, so you always have kind of a working project, this actually does allow you to make course corrections and to redesign portions of your software that aren't actually meeting specs or meeting operator needs. If you're doing continuous integration, right, and continuous is a misnomer. It doesn't have to be every second or continuously running, but it should be pretty much every commit should be looked at within a very short amount of time. Every commit should build, right? So if you're doing C or C++, no syntax errors, no compile errors. It should build mainline on an integration machine, so when added to the rest of the current system, it should work. You need to keep the build fast. So when we were talking about testing, we were talking about the difference between exhaustive unit testing and smoke tests and why they're both good regressions. You need to be able to keep the build fast if you're going to be doing something continuous. Put in as much detail as you can, but if your continuous test takes 7 hours to run, it's not really useful for people who are trying to commit every 5 minutes. So, you have to balance the number of tests you're running on a continuous level, as things are checked in with your actual commit cycle. Now, that doesn't mean that you shouldn't be doing regressions on the entire system, right? You should be running regressions on a periodic basis, maybe once a day, and that should be your exhaustive suite of tests, so that you have, so that you can capture more detailed, things may be harder to catch within some short time period on the order of a day or something like that. And then you should test in a clone of the production environment. So if your production environment needs a massive database, you should have some subset of data for that to represent that massive database. And hopefully you're going to also have automatic deployment. So as you get to the point where you've looked at the changes, you've built the changes, you can deploy it out there and everyone can get the latest executable. So none of your people are held up because only some select group has access to the latest and greatest, and they're working 3 versions back, and any changes they make still aren't going to be correct because they have to be brought into the main line, brought in line with what everybody else is doing. Okay, this, I guess we kind of said this. Daily, you should be compiling your working executable on a daily basis, and you should be doing exhaustive tests on that. And then your continuous integration server that's running continuously, it should pull down your latest repo and build all your resources. And this should be without need for intervention, at least to the extent you can get away with it. Unit tests, smoke tests, some functional tests can all be automated. The more things you can automate, the better off your testing is going to be, because the more things you can automate, the less man time it takes, right? Once you push in something, if you can run a big subset of your testing on it, that requires no additional person time, except to correct the errors that inevitably creep into the code. So this means that your team can be maximally productive, right? You don't have to have somebody sitting there whose only job is to press button 7 8 times in a row and then press button E, right? Free up your resources by using these automated test systems. And like we saw in Python, and like we'll see on CMake or CTest, there are a lot of systems out there that can allow, and Jenkins and Travis and all of these systems can help you do this in a very efficient manner, and they're more reliable than having your own crew run their tests manually. We talked about a stub. A stub is just a controllable replacement for an existing software unit to which your code under test has dependency. In other words, you have code that either isn't available or hasn't been written yet, but you have scoped out what you want some of its outputs to be, and so you write something that returns some of those outputs at different times for your different testing, so that you can pretend you have the whole system written and test pieces of code that depend on your stubbed code before the stubbed code is actually developed or perhaps even completely understood. Or maybe it results from difficult to control events, certain sequences of keystrokes, certain timing, etc. And this can be used, networked databases. You can stub out your database. You can write multiple threads, so you can test your program in a threading environment. You can use it to simulate access to memory. It's useful for legacy systems as well. So you're trying to pull something out of a legacy system, and you're trying to replace a part of the legacy system. Well, you can do a stub for the parts that you don't need to replace until you can actually get to the point of replacing them. And a mock object is the same, is similar at least. It's kind of where a stub is a participant in the test case. A mock object essentially looks at the outputs from your system and decides whether, based on the simulated outputs, it should pass or not. And again, before you actually have all of the system written. And that's useful for interaction testing. You're supposed to have a person there at the keyboard, but that would be a waste of time, and you can't do that automated. So you write a mock object to sit there and pretend to be the user and look at what comes out and is presented to it. And it's good for forcing things. It can look to make sure that all of your statements have been executed and covered. Again, there are a lot of ways of doing this. CMake with CTest, that's the one that we're going to kind of focus on. You're going to focus on in your lab. I'm not going to focus on that now. Travis CI, Jenkins CI, Circle CI, GitHub Actions, GitHub Actions, and GitLab all have software support for this kind of continuous integration, continuous deployment type of thing. All right, let's do a quick walkthrough. And actually, I may have time to do this. I've got about 5 minutes. If you go to that same place, the same place we had the READMEs, there is this GitHub quick start for GitHub Actions. Add GitHub Actions workflows to an existing repository in 5 minutes or less. And we have less. So we will actually try to do this. I am going to go to GitHub. Let's see. I want to pull this down so I can read it. And we're going to go to github.com. And let's see, let's do a stop. Okay, you don't have to get any bigger than that. That's fine. We'll go to my unknown repository. If you remember, unknown was just a repository to show you how to create a repository. It has one thing in it, which is contributions guidelines that says this is the guidelines, which is neither good English nor good Markdown. But you go into your repository. You can click on Actions. Right? Google makes this really pretty easy. I'm going to go into, you want to set up a workflow to set up GitHub Actions. So we will start from the simplest workflow. We'll click on set up this workflow. And what we're going to want to so this is just the basic workflow, and what you'll see is that in your unknown directory, or in whatever directory you have, it's now created a .github directory and a workflows directory, and this will be a workflows for all of your different workflows. And we'll just type in here linting. Sorry about that. I was actually looking for the linting one, and apparently I have bollocksed that up. I'm going to leave this page and start over again, see if I get to the linter. And then if I don't get to the linter, this action, by the way, will just echo some stuff whenever you execute it, but it's not the one I actually wanted. Okay. And apparently between getting started with this and finishing up the slides, well, I don't want to dig too far into our presentation time, so I think maybe what I will do is find the linter again this time. All right, yeah, I'm going to yeah, I don't want to waste any more time with this. I will do the linter for you, but we can set up a simple workflow here. This is a basic workflow. I'll just call this basic. We're going to do it on a push or on a pull request to master. It runs on Ubuntu latest, and I think all this does is just echo things out. So basically, we can save that. We can start the commit for this, and this is kind of a no-op. And we can commit it. And the way we have this set up is we have it set up to actually go on any push or pull request. We just push to master, so we should actually be able to come in and see that creating the basic YAML is actually running. So that's really all there is necessary. Anything you put in that .workflows directory will actually run, and then you can come down here and you can see what it actually did, and it will tell you that it succeeded in 3 seconds. Nothing it did here is actually worthwhile. I will get the linter back for the next time, but it just gives you all of the steps that were done on your job. And if we were to then go in and push to the repository, it will give us information on or do a pull request. It will give us information on the pull request as well that we can use to evaluate before we actually decide whether to do our merge or not. So it's just really simple to get the CI/CD working there, and they do have templates for everything, or for a lot of different things, including CMake, which you'll use on Thursday, and hopefully for lint that I'll be able to find. Again, last time I'm kind of befuddled because on Tuesday of last week, that was the recommended action that came up for me, given that everything here is just a very simple text files. But we will walk through it and find it. Anyway, that's all we have. I think at this point, right, we talked about some people coming up and presenting. So if we have a representative from the group 0006 Hong J8, I think this is Zach. Zach, do you want to come on up? And we'll invite you to the room, and you can kind of talk to us about your stuff. I'm going to give you a note. I'll say something at like 3 minutes, I think. Okay, I saw your hand up there for a second. Oh, okay, good. Timer.